This is section 1.4 part B, and we'll be concentrating on applications or modeling using quadratic equations. In our first example, a ball is thrown vertically upward with initial velocity 96 feet per second. The distance s in feet of the ball from the ground after t seconds is s of t equals 96t minus 16t squared. And our first question is, how long will it take for the ball to hit the ground? Well, first of all, I can kind of imagine what the graph of this function would look like. Certainly, just based on the equation itself, it's an upside down parabola. But I know that the ball is going to start on the ground and it's going to end on the ground. And so over time, it would look something like that. Here's my function, s of t. My goal is to figure out when the ball hits the ground, so I'd actually like to know what that point right there is. Now notice at the time the ball hits the ground, s of t is equal to 0. So if I plug 0 in for s of t in my original equation, I can figure out the time that this occurs. Let's do that now. 0 equals 96t minus 16t squared. And I believe I'm going to be able to solve this one by factoring. I can factor out a 16 and a t. That gives me 6 minus t. So either 16t equals 0 or 6 minus t equals 0. And first one gives me t equals 0. The second one gives me t equals 6. Certainly 0 would be the starting point when the ball first leaves the ground. So the one that I'm interested in is the 6. After 6 seconds, the ball hits the ground. Our second question asks, for what time interval is the ball more than 128 feet above the ground? So I want to know, when is my height, s of t, greater than 128? Well, s of t is 96t minus 16t squared. And I want to know when that's bigger than 128. Let's see. It would be a good idea to get this inequality to have 0 on one side. And so I'm going to go ahead and I'm actually going to move everything over to the right. I prefer to have that t squared term have a positive 16. So I would have 0 is greater than positive 16t squared minus 96t plus 128. Looks like all of my coefficients are divisible by 16, so let's try factoring and see if it gets us anywhere. We're now going to solve the related equation, 0 equals, and I'm going to factor the 16 out first of all, which gives me t squared minus 6t plus 8. And I think I can factor that one. T squared has to be t times t. A sum of negative 6 and a product of positive 8 would be negative 2 and negative 4. So my test points are t equals 2 and t equals 4. Let's check on those. All right. I'm going to check everything back in this equation right here. Or actually this inequality, I should say more precisely. And the first thing I'm going to do is choose a test value of 0. If I plugged 0 in for t, my inequality would say 0 is greater than 128, which is certainly false. If I plug in a test value of 3, I'll leave it to you to check the arithmetic, but the equation does come out true. And if I tested 5, again, I'll leave it to you to run the arithmetic, but this inequality is false again. And so I'm going to conclude that the ball is more than 128 feet above the ground in here, between 2 and 4 seconds. The last part of this problem asks us to find the highest point reached by the ball, and then determine how long it takes the ball to reach that point. Well, if I just draw my sketch one more time here, the highest point reached by the ball is really the vertex. And we know how to find the vertex of a quadratic function. In this case, it's in standard form, so we'll want to use our vertex formula. Just a reminder, S of t is 96t minus 16t squared. Or if I were to rewrite that in kind of the normal order, negative 16t squared plus 96t, I can say the vertex would have an x, or in this case a t value, of minus b over 2a, which is negative 96 over 2 times negative 16, which comes out to 3. So after 3 seconds, the time that is 3, the ball has reached its highest point. To find that highest point, I would plug the 3 back into the function. S of 3 is 96 times 3 minus 16 times 3 squared. And let's see, that comes out to 144. So this ball reaches its highest point of 144 feet in the air after 3 seconds. In the next example, we're looking at the U.S. birth rate, capital B, for unmarried women. The units are births per 1,000 unmarried women. Of age A, can be modeled by the function B of A equals negative 0.31a squared plus 16.54a minus 151.04. First of all, we just want to find the birth rate for unmarried 20-year-old women. So I've been given an A value here. I've been told that A is 20. And if I plug that into the function, B of 20, putting 20 in for all of the A's, and then grabbing my calculator, oops, which I've got to do here, I came up with 55.76. So we can say there's approximately 56 births per 1,000 unmarried 20-year-old women. Okay, the next question. At what age, or what ages, is the birth rate for unmarried women at least 35 births per 1,000 unmarried women? So this time I want to know, when is B greater than or equal to 35? When is the birth rate at least 35, greater than or equal to 35? And I'm going to go ahead and put this in here. Here's the B. And I want that to be greater than or equal to 35. Now once again, I always, when I'm working with quadratics, would like 0 on one side. So I'm going to subtract off the 35 to get the 0 on the right-hand side. Like that. Okay. We'll solve the last one of these by hand, by finding the related equation and testing on a number line. We know that we can also solve these using a calculator, and I'd like to do that now. Okay, so here's my calculator. And I think I'm going to rethink that getting this to 0 side. I'm going to use this function for something else in a little bit. So it would actually be a good idea for me to not alter my original function at all. So let's put the original function b into our calculator. And that was negative 0.31. And ours is a, but the calculator will have to use x squared plus 16.54x minus 151.05. And I'm going to choose to use the technique of putting the right-hand side, the 35, in the other line of the calculator under my y2. And let's see, let's set our window a little bit here. Let's see, I know that my x's are really a's or ages, so I'm going to go 0 to 100 for age. Count by tens. The y's are the birth rates. Let's go 0 to 100 on those as well and see what happens. Once again, I'll count by tens. And I'm going to graph that. Okay, there we go. So I can clearly see that in the center part, the birth rate is larger than the 35, which is the horizontal line here. So I need to know where are the intersection points on this. To get the intersections, remember that we do second calc, and I go down to option number 5, which is intersect. And for first curve, we could say enter. For second, enter. And then I'm going to move my cursor over to the left to get near the leftmost intersection point. And enter. And that's at about 16. X or A is about age 16. If I do the other intersection point, so one more time, second calc, option number 5 for intersect, and first curve enter, second curve enter, and this time for my guess, I'm going to go over near the other intersection point before I push enter. That looks like about age 37. So between the ages of 16 and 37, the birth rate is above 35 births per 1,000 unmarried women. The final question here is, at what age is the birth rate for unmarried women at its highest? And what is that birth rate? So once again, what we're really looking for is the vertex of the parabola. Going back into my y equals, I no longer need the 35. And so I'm going to go ahead and I'm going to get rid of that one. Go down here and clear that so that I can graph just the original function. And what I'm now looking for is this maximum point, the vertex of the parabola. So if I use a technology method to do that, I would say second calc. And this time I'm looking for option number 4, the maximum. I need to give the calculator a left and right bound. So I'm going to start by using my left arrow key until I can position my cursor very definitely to the left of that vertex. Maybe over there. Enter, and then using my arrow keys again to go to the right of the vertex, enter again, and for the guess I just enter. And we can see here the maximum is at about age 27 with just about 70 births per 1,000 unmarried women. So at age 70, excuse me, at age 27, makes more sense. The birth rate is highest at about 70 births per unmarried woman, per 1,000 unmarried women. Throughout the remainder of this video, I'll continue to sometimes do things by hand and sometimes by calculator. It's a good idea to know both techniques. When you take tests for me, there will be certain problems that I'll specify must be done showing your work by hand, but on others, I won't give you any specific directions, so you're welcome on those to use your calculator as much as you like. All right, in the next example, we're going to look at a problem from economics where the complete model isn't given to us. We have to kind of construct it for ourselves. We're told that the revenue from sales of a particular item is the number sold, X, multiplied by the price of each item. Makes sense. Revenue is number sold times price. However, there's also a relationship between the number sold and the price. This is the demand equation. If higher prices prevail, usually fewer items are bought. When the price goes down, the demand goes up. So that kind of thing. Market research for a particular brand of phone shows that at a price P, the number of units in thousands sold will be X equals 800 minus 2.5P. The first thing I want to do is find the revenue function for this phone as a function of price. So again, R of P equals XP was given to me. And I also know X is 800 minus 2.5P. So I'll replace the X with 800 minus 2.5P. And then distributing is going to give me 800P minus 2.5P squared. So first order of business here is to take this quadratic function, and for the prices listed in the table, I'd like to calculate the revenue using the equation that I just found. So first I'm going to plug 50 in for P, and then 100, and so on. And when I did this, I got the following values. $37,750 at a price of $100, $55,000 in revenue. At a price of $150, $63,750. If we charge $200, revenue becomes $60,000. At a price of $250, $43,750. And at a price of $300, it becomes $15,000. So we can see that for a while, our revenue is going up. Right? And here, our revenue is increasing. At those low prices, we're selling quite a few phones. We're making more and more money. Then, down through here, our revenue starts decreasing. The prices become to the point where fewer people are buying the phones, and so we're not making as much. I'd like to show you a quick way of getting these values on your calculator as well. If you've never used a table feature before, it's really handy and it's a fast way to come up with these numbers. Let's go ahead and type the function, the equation itself, into our calculator. It was 800p, so we'll put it in as 800x minus 2.5x squared. This time, rather than go to a graph, I'm going to go to a table. And the first thing you're going to want to do is set up your table. So above the window key, it says Table Set. And it goes Second, Table Set. And I don't care about anything here except under this independent variable. I'd like to change it to say Ask. Okay. Once this is set, if you don't change it, it'll be like that forevermore, so you'll be able to use this over and over in this way. Okay. I'm now going to go to a second table. Table is above the graph key. And it's now going to allow me to put any x values I like in here, and it will give me the output. So let's put in the numbers that we had. 50, enter. 100, enter. 150, 200, 250, and 300. You can see that the values that the calculator returns are the exact same ones we got by manually plugging in those numbers. But it's a nice, fast way to do it, so I wanted to make sure you had a chance to see that. The final question in this example asks, how should the price be set in order to maximize the revenue? Notice that in our table, the largest revenue happens when our X value, or our price rather, is $150. At that point, we see the largest revenue. But we don't really know if that's the actual maximum or if the maximum could be a little bit less or a little bit more than 150 at a value that wasn't evaluated in this table. So we're going to go ahead and do this one by hand again. I'm going to use algebra to see if I can maximize my revenue. My function R of P, and I am going to rewrite it in sort of the standard order, descending order, was negative 2.5 p squared plus 800 p. And in order to find the maximum, I know that that's really the vertex. So I'll use my vertex formula. The x is actually the p here, equals minus b over 2a, would be negative 800 divided by 2 times negative 2.5. And when you run those numbers through your calculator, you come up with 160. So we're close to the 150 that we saw in the table, but the actual maximum revenue is $160 price. If I want to know what the revenue itself is, I'll just plug that 160 in for P in that equation. And I ran through those numbers and I actually got 64,000 when I did. So the price should be $160. And that will yield the maximum revenue of $64,000. In the next example, we plan to build a fence to enclose a rectangular garden, and we're going to separate the enclosure into 2 sections using a fence down the middle, parallel to the short side of the rectangle. You have 750 feet of fencing to use. We're supposed to first find a function a of x that represents the area of the function. Excuse me, that shouldn't be the function, that should be area of the garden. So we're supposed to find the area of the garden in terms of the length of the short side of the rectangle, x. So let's draw a picture of this. Here's our rectangular garden. And here's the fence down the middle. The short side we're supposed to label x. There'll be 3 fences of length x. And for right now, I'm going to use y as the long side of my rectangle. I do know a relationship between the x's and the y's. Namely, I only have 750 feet of fencing in all. So I know that 3x plus 2y can equal 750. I'm going to solve that equation for y. First, I'll subtract the 3x and then divide by the 2. So y is negative 1.5x plus 375. So let's put that in. Let's write it down once. All right, area now, a of x, is going to be the length of the rectangle times the width. That would be x times negative 1.5x plus 375, or negative 1.5x squared plus 375x. So there's my area function for this rectangle. The next question says, find the dimensions of the rectangle that give a total enclosed area of at least 15,000 square feet. So I would like that area to be greater than or equal to 15,000. Well, let's see. A is negative 1.5x squared plus 375x, and I want that greater than or equal to 15,000. If I wanted to use technology on this one, I could now graph both sides of that inequality and then take a look at the graph to see where the left side is bigger than the right side. However, in this case, I'm going to go ahead and do this one by hand. As I said, I'll kind of do both methods back and forth to give you some experience. So I'm going to go ahead and I'm going to write the inequality, bringing the 15,000 over, so I have it greater than or equal to 0. When I work by hand, I always start by solving the related equation. So I'm now going to solve as if this were an equation, an equality here. Okay, let's see. I'm going to go ahead first of all, and I'm going to factor out that negative 1.5. And when I do, when I divide everything by negative 1.5, I get x squared minus 250x plus 10,000 equals 0. And if I now try to factor this, I know I'm going to start with x times x, and I need two numbers that add up to negative 250 and multiply to 10,000. I think 250 will do that, both negative. And so I get x equal 200 and x equal 50 as my test points. All right, to do the test, I'm going to go back to this function right here, the inequality. And I'm going to start by plugging in 0 as my first test point. And I can certainly see that if x is 0, I would get negative 15,000 greater than or equal to 0, which is false. Once again, I'll leave it to you to do the arithmetic, but if I were to plug 100 into that inequality, I would get a true statement. And if I were to plug in perhaps 300, I would get a false statement again. So, for x between 50 and 200, I get a total enclosed area of at least 15,000 square feet. The last question asked us to find the dimensions of the rectangle that enclose the maximum possible area. Whenever I see the word maximum or minimum, I'm always thinking about the vertex of the parabola. So I'll go back to my original area function, rewrite it here. It was negative 1.5x squared plus 375x. And again, I could graph this and find the vertex using that maximum feature, but this time I'm going to do it by hand. I'm going to say x is minus b over 2a, which would be negative 375, divided by 2 times negative 1.5, and that happens to come out to 125. That's one of the dimensions. It's the width of the rectangle. To get the length of the rectangle, I also need a y value. So if I come back up and say, well, I actually had this expression here for y. So if I plug 125 in for x, let's see, I got 187.5 for that. So my conclusion is that the maximum area will be enclosed if I have a length of 187.5 feet and a width of 125 feet. We have a couple more examples, and the last two examples will be using data that we'll have to enter into our calculator. So I'm going to make one more video for that. This one's getting a little lengthy, so if you need to take a break, you can do that, and then come on back and we'll do the last video regarding the data entry.